Hello, and welcome to part 2 of our mathematical dive into waves. In this episode, we'll be looking at the oscillation of a two-dimensional membrane, which is one step up from the one-dimensional string that we considered in the previous episode. This will lead us to the two-dimensional wave equation. Following this, we will define the three-dimensional wave equation with sufficient motivation, and then show some examples of real-world phenomena that obey it. Finally, we'll discuss how we might be able to solve these equations and settle on some differential equation terminology. We first look at the oscillation of a membrane. Suppose we have a taut membrane with tension T and mass density mu. Here, mass density is the mass per unit area. We define tension in the following way. Suppose we have a little area on the membrane. Consider the tensile forces acting on the perimeter of that area. Looking very closely at one part of that area, where the perimeter looks like a straight line, and the forces due to tension act to one side, all virtually in the same direction, we say that if the length of this line segment is delta S, and the total force exerted on the segment is F, then we say that that total force F has magnitude T delta S. That is, we're defining tension as the force per unit length on a segment of the perimeter of an area on the membrane. We now impose some axes, where x and y are more or less parallel to the membrane. U points in the transverse direction, that is, perpendicular to the membrane, as that is the direction in which we presume the membrane is oscillating. We use U to represent the membrane's transverse displacement, and as a consequence, U is a function of x, y, and time. To obtain an equation of motion for the membrane, we will consider the net transverse force on an area element that's aligned with the coordinate axes of tiny dimensions delta x, delta y. And yes, I've misspelled transverse. We now take a closer look at the area element, and I've taken a note of the xy coordinates of each corner. Tensile forces due to the tension act on all edges of this area element. On the two edges that are parallel to the y-axis, the tension acts more or less parallel to the xu plane. On the two edges that are parallel to the x-axis, the tension acts more or less parallel to the yu plane. If we let F sub x denote the net transverse force on the area element due to the forces on the two edges parallel to the y-axis, here labeled in green, and let F sub y denote the net transverse force on the area element due to the forces on the edges that are parallel to the x-axis, then the total net transverse force on the area element will be the sum of F sub x and F sub y. Here we have labeled it as F sub un, standing for unbalanced force. F sub un is the total unbalanced transverse component of all these force vectors. We first calculate F sub x. To achieve this, we partition the area element into thin strips. The length of these strips is parallel to the x-axis. We suppose that each strip is of width delta y prime. And keep in mind that delta y prime is much smaller than delta y. We call the resultant forces acting on each end of a strip F1 and F2, and we keep track of their directions by noting the angles they make from the positive x-axis in the xu plane. Since the tension is the force per unit length, and the lengths in question are both delta y prime, we conclude that the magnitude of both these forces, F1 and F2, is equal to T times delta y prime. Using trigonometry, we see that the net transverse component of force on this strip due to the forces F1 and F2 is equal to T times sine theta 2 minus sine theta 1 times delta y prime. Just as when we considered the one-dimensional string, we assume that these oscillations are smooth and small, meaning that the angles theta 1 and theta 2 are very small themselves. This lets us do a small angle approximation on sine theta 2 and sine theta 1, allowing us to write them as tan theta 2 and tan theta 1. Here we notice that tan theta 2 will be equal to the partial derivative of u in the x direction, evaluated at the appropriate point, x plus delta x, y plus y prime. The purpose of the y prime is to specify which strip we are in. It'll equal some integer times delta y prime. Similarly, for tan theta 1, we can also write that as the partial derivative of u in the x direction, but this time evaluated at the point x, y plus y prime. Substituting these in, we get this expression for the net transverse force on the strip due to the forces at each end. Now, the area element is comprised of all the strips, so F sub x will be the sum of all such forces across all the strips. We want to take the limit as delta y prime approaches 0, and the number of strips approaches infinity. So this sum is actually a Riemann sum and converges to an integral, where we integrate over y prime between 0 and delta y to take us across the entire area element. T is just a constant, so we can pull it out the front. Also note that our delta y prime became the differential form dy prime during the limiting process. We now have this expression for f sub x. We'll now proceed to evaluate this integral and simplify the expression. We begin by Taylor expanding the first term of the integrand in delta x about x. We have explicitly written out the first two terms of the expansion and grouped all terms of order 2 and higher into the big O notation. We see that these two terms cancel, and so our expression becomes the following. We then split up this integral into two, where we have pulled out a delta x in the first term. While we don't need to, we will try to be careful when tracking our finite differences. In this integral, we can imagine expanding the integrand in y prime, and so all the terms with two delta x factors, that is, the contents of this integral, become terms with at least two delta x factors and at least 0 y prime factors. The reason for writing y prime to the power of 0 in the big O notation after the semicolon is done because we will be integrating in y prime, and so the powers of all the y primes that appear will increase by 1. Writing out the right-hand integral once again, we can evaluate the integrand. In doing so, the y prime power in the big O notation goes up by 1. And so before plugging limits in, we see that this will be a collection of terms with at least two delta x factors and at least one y prime factor. These terms vanish when we plug 0 into y prime, and y prime becomes delta y when delta y is plugged into y prime. And so these terms can be written as follows, once the limits of integration have been dealt with. That is, this integral has become a group of terms with at least two delta x factors and at least one delta y factor each. We now sort out the other integral. We do so by Taylor expanding in y prime about y. Here we have explicitly written out the 0th order term and grouped all terms of order 1 and higher together. After integrating, term by term, and using power rule, each term gets an additional y prime factor. Plugging in our integration limits, our y primes become delta y, since all terms vanish when we plug 0 into y prime. Substituting this back into our expression for f sub x, we have the following. Notice that, when substituting back big O delta y squared, terms of order delta y squared and higher, it has absorbed t, and, due to the extra delta x prefactor out the front of the integral, become big O delta x delta y squared, where, once again, to clear up this notation, we can read this as terms with at least one delta x factor and at least two delta y factors. And so we've expressed f sub x as a power series in delta x and delta y, and we see that the most significant term, which is the one we were chasing, is equal to t delta x delta y, the second derivative of u in the x direction, evaluated at xyt. Again, there was no need to be as, quote, rigorous as we were with the big O notation, because we could simply recognize that as higher order terms and throw them out immediately. But this is good practice, because sometimes the little finite differences, such as delta x, do come back to bite. Recall that the net transverse force on the area element was equal to f sub x plus f sub y. We now know what f sub x is. Finding f sub y is very similar, and you could even use a symmetry argument to show that it must be the same as f sub x, but all the x's and y's are swapped, except for in the input to u. But as an exercise, I'll let you derive the expression for f sub y. We now know what the total unbalanced force is, but recall that we're looking for an equation of motion, and force is proportional to acceleration. By Newton's second law, the force is equal to mass times acceleration, in this case acceleration in the transverse direction. We can write the unbalanced force as equal to mu delta x delta y, that term is for the mass, the density times the area of the surface element, multiplied by the second time derivative of u. That second factor is the transverse acceleration. We now equate this expression to f sub x plus f sub y. Notice that we have factored out t delta x delta y from both spatial derivative of u terms. We next divide by mu delta x delta y, and get this. We now see that the only finite differences, delta x and delta y, are those in the big O notation, where we have appropriately dropped their orders. Because they are going to be infinitesimal as we take the limit as delta x and delta y approach 0, we can ignore them. We also define the parameter c as equal to root t divided by mu, as we did with the string when deriving the one-dimensional wave equation. Knocking off those last terms, and doing the substitution for t over mu, which would be c squared, we get this expression. Next, we can divide by c squared, and bring everything to the left-hand side. And we're left with this. This is the two-dimensional wave equation, and the oscillating membrane satisfies it. We can define a differential operator, W2D, standing for wave equation two-dimensional, and then that lets us write the wave equation more concisely, like so. And it's important to remember that u is a function of x, y, and time. Now let's modify the two-dimensional wave equation to include a term on the right, ρ, a function of x, y, and time. As with the one-dimensional wave equation, ρ is a source, or source function, or driving force. Here's a good way to visualize it. The source function is affecting the membrane by exerting a force in it. And this leads us to the general two-dimensional wave equation, which is the two-dimensional wave equation with source. Compare this to the one-dimensional wave equation with source. You can see the similarity. The two are the same, except the input function has an additional value, and in the two-dimensional wave equation case, there is an extra term in the differential operator, that is, a negative d2y. You can see how similar they are if we just look at the wave equation operators themselves. So now we start to ask what the three-dimensional wave equation could be. Well, let's go back to our previous wave equations. When we considered a string, we were led to what we called the one-dimensional wave equation, since the string was very much one-dimensional. This can also be seen in the fact that the one-dimensional wave equation only involves one spatial input for the input function, that is x. But surely, the string requires another dimension to oscillate in, right? The oscillation should exist in a two-dimensional plane. Not necessarily. What we were calling the amplitude does not need to be physical displacement, and it is for this reason that when drawing diagrams for the oscillating string, I did not use another coordinate axis like z. I used u directly, to help induce the abstraction, if you will. U could be anything. It could be electric potential, air pressure, or something else entirely. U is what we call a scalar field, which is simply a function that assigns a value to every point in space, in this case, at each point in one-dimensional space. Similarly, when we consider the membrane, this led us to the two-dimensional wave equation, since the membrane was two-dimensional, and appropriately, the corresponding differential equation involved two spatial inputs, x and y. Again, we did not need a third dimension for the oscillations. Because u did not need to be physical displacement, the third dimension is not required. And thus, we don't need to push the number of spatial dimensions in our universe to consider the three-dimensional wave equation. What would that be? We would like something like a three-dimensional wave equation operator acting on a function u, representing amplitude, but not necessarily physical displacement in a fourth dimension, that takes in four variables, x, y, z, three spatial ones, and time, with some sort of source function with inputs x, y, z, and time. We recall our natural definitions. The one-dimensional wave equation operator was 1 over c squared d2t minus d2x. The two-dimensional wave equation operator was defined as 1 over c squared d2t minus d2x minus d2y. The pattern here is quite obvious. For every coordinate that we have, for every Cartesian coordinate in our space, we have an extra differential operator, which is the second derivative with respect to that coordinate. So it seems completely natural to define the three-dimensional wave equation operator as 1 over c squared d2t minus d2x minus d2y minus d2z. Now, the differential operator d2x plus d2y plus d2z has a special name. It's called the Laplacian, and is given by this symbol. Thus, we can write our three-dimensional wave equation operator in shorthand using the Laplacian operator. And in fact, we can treat the two-dimensional and one-dimensional wave equations as having lower-dimensional Laplacian variants, which we can label as one-dimensional, two-dimensional, and, although we usually won't write this, three-dimensional. In this sense, the n-dimensional Laplacian operator we could define as this sum. That is, in Cartesian coordinates, it is the sum of all second differential operators with respect to each coordinate. And if we want to have a little bit more fun, we could define the n-dimensional wave equation as 1 over c squared d2t minus the n-dimensional Laplacian. Thus we have our three-dimensional wave equation with source. Note that instead of writing the triplet xyz, we've used a position vector, r vector, just to ease the notation a bit. And in shorthand, we can write it like this. To be clear, it is actually possible to derive this as the equation of motion of some sort of oscillating three-dimensional volume in four-dimensional space, similar to how we worked with the vibrating string or membrane. But there's no way in hell I'm going to do that because it seems extremely tedious. But if you want to do that, I'll leave it as an exercise. So we have derived the three-dimensional wave equation for a scalar field. Are there any such fields in nature that satisfy it? Well, yes. One is the acoustic pressure P. To be clear, acoustic pressure is a local deviation from the ambient pressure. This shouldn't be too surprising because sound propagates in waves of acoustic pressure. If we now include a source term ρ would represent a source of sound, like a speaker. As a gut check, you could imagine a speaker in a room which would act like an oscillating point source. We would expect waves to move radially outward from the speaker, and if we were listening to the speaker, we could record it with a microphone, and we would expect the microphone to pick up a signal something like this, where the acoustic pressure at the point of the microphone would oscillate as time went by. While I won't go through the details now, Maxwell's equations for electromagnetism can be used to show that all the fields from electromagnetism satisfy wave equations. These fields are the electric potential phi, the magnetic vector potential A, the electric field E, and the magnetic field B. We are already familiar with scalar fields, such as phi, but A, E, and B are actually vector fields. A vector field is simply a math object that assigns a vector to each point in space. This triangle symbol is actually called the gradient operator. It is a vector operator, and, in Cartesian coordinates, is equal to each basis vector multiplied by the differential operator with respect to that coordinate. And so applying the gradient operator to a scalar field like phi would return a vector called the gradient of phi, whose ith component would be the derivative of phi with respect to the ith coordinate. The gradient of phi appears in the electric field definition. And also, we can perform a vector cross product between the gradient operator and a vector field, such as A. And in that case, the ith component of the resulting vector field, or actually pseudo-vector field, if we want to be technical, would be equal to the Levi-Civita symbol epsilon ijk multiplied by the derivative of the kth component of A in the jth direction, where we sum over both j and k. Each index is summed from 1 to 3. This Levi-Civita symbol is defined as follows. Epsilon ijk is equal to 1 if ijk is an even permutation of 1, 2, 3, and negative 1 if ijk is an odd permutation of 1, 2, 3, and 0 otherwise. This might look a little daunting, but it's a very convenient and shorthand way of writing down cross products. The gradient operator, crossed with a vector field, is also called the curl of that vector field. And so we see that the magnetic field vector is defined as the curl of the magnetic vector potential. And now it should be clear why the Laplacian looks the way it does. It can be thought of as a dot product between two gradient operators. We now look at the wave equations that these fields satisfy. The electric potential phi satisfies the three-dimensional wave equation, where the source term is charge density ρ, which is a scalar field, divided by the permittivity of free space, epsilon naught. The magnetic vector potential A also satisfies the three-dimensional wave equation, where the source term is equal to the permeability of free space μ0 multiplied by the charge current density, which is a vector field. It may look a little bit scary having a vector field in our differential equation, but this simply means that the corresponding differential equation for each component holds. And when we see the Laplacian acting on a vector field, we just mean that it is a vector whose ith component is the Laplacian of the ith component of A. And finally, we have the wave equations for electric field and magnetic field. These look a little scarier, but it is still the honest-to-good wave equation operator on the left-hand side, just with more complicated source terms. We can use our more shorthand operator notation to really drive home the symmetries of nature. And in these equations, c is actually equal to 1 over the square root of epsilon naught mu naught, which comes out at about 3 times 10 to the 8 meters per second. This is the speed of light, and indeed, it is no coincidence, because light is an electromagnetic wave. So we have seen that many fields in nature satisfy the three-dimensional wave equation. So this differential equation, where the three-dimensional wave equation operator acting on a field u is equal to some sort of source term ρ, is a very important one to be able to solve. But how do we solve it? If only there was some sort of inverse operator that we could apply to both sides, to cancel the three-dimensional wave equation operator on the left and extract u. The solution to u would then be the inverse three-dimensional wave equation operator acting on the source function ρ. But how do we know that such an inverse operator exists? And what limitations would this method have? The answers to these questions will come soon enough, but first, let's settle on some differential equation terminology. A so-called homogeneous differential equation, involving a function f, involves only derivatives of f, and f itself. We typically put these terms on the left of a differential equation, so homogeneous differential equations are identified by a 0 on the right-hand side. An example includes this differential equation, where the time derivative of f plus the second x derivative of f equals 0. On the other hand, non-homogeneous differential equations involve other terms, like free constants or other functions. These are typically put on the right, and so the right-hand side is not 0. An example would be the differential equation that we just looked at, but with the term ρ that could be a function, or constant, or anything else. If we are dealing with a linear differential operator L, then the non-homogeneous equation, L acting on f equals ρ, is said to have the corresponding homogeneous equation, L acting on f equals 0. And finding all solutions to this differential equation amounts to finding all homogeneous solutions, and then finding at least one, which is usually the simplest, non-homogeneous solution. By linearity, this means that we would know all non-homogeneous solutions. This abstract explanation of solving non-homogeneous differential equations certainly does not scream intuition, so let's try visualizing it. Here we have the surface of a pond. Assuming that u, the field representing the vertical displacement of the surface water, satisfies the two-dimensional wave equation, then the solutions for its motion will be the homogeneous solutions of said differential equation, perhaps subject to certain boundary conditions. And here we have sketched two possible solutions. On the left, the surface water is stationary and flat, whereas on the right, it is rippling. There need not be a source to cause the rippling, because we suppose that this is an eternal pond, so the rippling does not have a start point nor an end point in time. If we want to find the motion of the surface water when a rock lands in the pond, however, we must find a non-homogeneous solution to the differential equation where the source term ρ represents the rock striking the surface of the water. We have sketched a possible solution, but notice that it is for that of a rock striking an otherwise still pond. Equally, we could find the solution for a rock striking the rippling pond. In either case, the pond's surface water is a valid non-homogeneous solution to the differential equation. But, if we were trying to find one, we may assume the simplest case, which is the one where the rock strikes the otherwise still pond, since we can always add the rippling behavior by linearity, giving us the solution at the bottom right. Being able to always add homogeneous solutions is the reason why you can see a light bulb even if there's a source of charge messing with the electric field between you and it. Earlier, we asked if it was possible to find an inverse operator such that we could find the solution to the three-dimensional wave equation, or other differential equations, by applying that operator. The answer is yes, there is a way to do it, and we will develop a method for finding inverse operators soon enough. But I will also mention that our method will give us a particular non-homogeneous solution, and given the way we set up the method, the solution will be the simplest non-homogeneous one. And that is the end of part 2. In the next part, we'll be looking at developing the machinery to solve non-homogeneous differential equations in this way. That will involve the Dirac delta function, Green's functions, and convolutions. I hope you guys enjoyed this one.